Okay, today we're going to have a quick look at how to use matrices to solve equations, specifically simultaneous equations. Obviously, we're very familiar with simultaneous equations from sort of GCSE level, two variables, pretty straightforward, trying to find the coordinates normally where sort of two straight lines meet over, or maybe, a circle and a straight line if we're getting particularly funky, whatever it might be. Absolutely fine. We've probably also encountered three variable simultaneous equations in 3 dimensions. And the idea which we'd currently use is probably to try and sort of make x a subject of an equation and then substitute it all in it. It would get quite nasty, okay? Trying to do simultaneous equations with 3 different variables is going to be quite problematic for us using the same GCSE methods. And that's where matrices is going to come in. I want to start off by talking about this identity at the top. AB equals C, okay, where let's say all of those are matrices of some description. Using what we spoke about last week, the inverse sort of properties, we should understand that we can use this sort of approach to get an expression just for B. Okay, if we take a to the minus 1b, we can get, can't we, a to the minus 1c. Sorry, actually that should be a to the minus 1a equals a to the minus 1c. Obviously, once this is the identity matrix, that is just B, isn't it? Okay, so having got a matrix on its own, we need to work out B. We've got the inverse of A multiplied by C. Now, putting that into sort of context of where we're going today, let's consider the singular matrix x, y, z. If we have A multiplied by x, y, z equals V, and we're trying to work out x, y, z, i.e. the solutions of our simultaneous equations, we're going to put into practice this identity up top, and we're going to take inverses of A, and we're going to multiply that by whatever V is to get us our answers for x, y, z. Let's put that into an example. Here we go. We've got 3 simultaneous equations to start off with. Minus x plus 6y minus 2z is 21. 6x minus 2y minus z is minus 16. And minus 2x plus 3y plus 5z equals 24. Now, this is the key bit. We can write this as a matrix equation. Okay, all we're going to do is in our left-hand column, we're going to have all of our x coefficients, minus 1, 6, minus 2. In the middle, we're going to have our y coefficients, 6, minus 2, and positive 3. In our right-hand column, we're going to have minus 2, minus 1, and 5 for our z coefficients. And we're going to say if we times that by x, y, z, okay, which in itself is a matrix here, we are going to get our answer of 21, minus 16, and 24. Now, if you really wanted to, you could check this slightly. If you don't believe me that this is going to work, you could check this because, remember, n by m, our general format. This one here has 3 rows and 3 columns. It's a 3 by 3 matrix, and this one has 3 rows and 1 column. So it is allowed, isn't it, this multiplication? The other way around wouldn't be, would it? But the point is, if we do this, if we times this out, we're going to get minus 1 times x, we're going to get 6 times y, and minus 2 times z. So you can see that this is actually another way of writing the same thing, I hope. Now, this is our startup point, okay, for the whole question. We haven't actually done anything yet. We're just at the AB equals C setup, but we have changed our sort of just written simultaneous equations into a matrix equation. Now, here we go in terms of the actual sort of solution. We're going to focus on the matrix which we had, the coefficients matrix, and we're going to find its inverse. Now, we went through this last week, so I'm going to go through it relatively quickly, but remember the various stages. We're going to start off by finding the determinant of this matrix, which in this case is minus 189. Then we're going to find the matrix of its minors. Then we're going to employ the plus minus sort of cofactor pattern, which is here. And then we're going to transpose that matrix. Okay, so hopefully we've built up a little bit of fluency in that process anyway, and we should be okay to here. Now, going back to what we were just talking about, we need to input the inverse of our front matrix, our coefficient matrix, in front of our numerical solutions, which is going to be our other matrix. Again, the reason being is because we're allowed to do a 3 by 3 multiplied by a 3 by 1. We're not allowed to do it the other way around. So, putting this into practice, we're just going to multiply out all of this. Now, just a quick reminder, we're going to do 7 over 189 times 21, plus 36 over 189 times minus 16, plus 10 over 189 times by 24. And we're just going to times it out. Eventually, we're going to come out with a really, really nice clean set of solutions, which you're going to know are correct if they come out that clean. And obviously you can substitute them back in or indeed use the simultaneous equations mode in your calculator to check your work. Okay, but that's how we're going to employ matrices to solve simultaneous equations with 3 different variables. Now, very, very quickly, there's an example in the book which I'm just going to refer to. So if you've got your book handy, you can have a quick look at this. It's example 21. We're going to be called upon to form and solve our own simultaneous equations, as you have previously done, so it's nothing particularly new. But I just wanted to talk about the order of our various equations. Now, it's really important that we specify let x be this, let y be this, let z be this. And so in example 21, the x is going to represent the number of adult males, and mole rats obviously, y is going to be the number of adult females, and z is going to be the number of youngsters. Now, we're initially told that a colony of 1,000 mole rats is made up of all of these 3 different types. So our first easy equation to form is x plus y plus z equals 1,000. Our next fact is that there are 100 more adult females than males. Now what that means is that x minus y is in this instance going to equal minus 100, okay? You could have written this as minus x plus y if you really wanted to. It doesn't really matter either way. Okay, but the difference between the male and the female mole rats is going to be 100. And our third fact is going to be quite common. This is going to be using sort of multipliers for our percentage changes. 1.02 represents an increase in that male population. 1.03 and 0.96 represents a decrease of 4%, doesn't it? And we're going to equal 980. That's the total new population. So we can form these various equations. Now, once we're here, I'm going to sort of have to be quite small here. Apologies for this. We can quite quickly form our matrix, which we're going to use. And we're going to say that that multiplied by x, y, z equals 1,000 minus 100 and 980. Okay, and we're going to concentrate on getting the inverse of this and then multiplying it by this to work out what our x, y, and z values are. So really, really pleasing method here, I think, how to solve simultaneous equations using our matrices. I like it a lot. It's very quick and clean, much quicker than all of the stuff that we could faff around with. Now, the hard bit of this little exercise, I would suggest, is this idea of consistency. I would suggest that you get to grips with this flowchart as the easiest way to sort of start to understand this. Basically, the word consistency sort of refers to the number of solutions which we're going to have from our various simultaneous equations. Now, the ones which we've just looked at so far follow this aspect of our flowchart. They are non-singular matrices, as in the determinant is not equal to 0, which means, as I think we should all recall, that there is an inverse available. Okay, because there is an inverse available, it means we're going to be able to work out a specific set of solutions for those equations, as in there is one specific set of solutions for where that happens. Okay, so that's the ones which we've already looked at. Now, slightly more complex are the ones over here, where we actually try and find a determinant, and we realise that our determinant is 0, as in there is not an inverse. Now, at this stage, there is a choice between consistency and non-consistency. And I'm going to refer you to have a little look at the example in example 22 in your book. But what we need to do here is we need to eliminate one of the variables. Okay, if we start off with 3 equations, we're going to form 2 new equations where we have eliminated the same variable from those 2 new equations. Okay, and so let's say you've got equations 1, 2, and 3. You're going to use equations 1 and 2 to get a new equation 4, and you use equations 2 and 3 to get a new equation 5. But the point is we've eliminated the same variable from those 2 things. Now, once we've got those 2 new equations, if they are multiples of each other, okay, and you should recognise that when it happens, we're going to say that those are consistent. If they are not multiples of each other, they're not going to be consistent. Now, consistent, they're going to have infinite solutions. Non-consistent, there's actually going to be no solutions. Now, this next bit is the final step. There are 2 options which cause infinite solutions. Either our planes are going to meet as a sheaf, okay, or they're actually all going to be on the same plane. Alternatively, when there's no solutions, the options are prisms. Okay, all of our planes form a prism. And if we have, for example, a triangular prism, obviously this is a 2D sketch of three dimensions, okay? But you can see there's no one point which satisfies all three planes, okay? There's nothing which satisfies them. They join up as twos, obviously, but there's no point for all three. And the other option is parallel, okay? If we have one parallel plane, okay, again, there's not going to be a point where there are all three of them meeting simultaneously. Now, it helps me. I think we need to be sort of relatively happy with this idea of working out if it's consistency or non-consistency by eliminating a variable. It helps me to visualize the various different things on the calculator. So very quickly, I just thought I'd show you that. You can go to menu, and then you need to scroll down ever so slightly to 3D graph. And on 3D graph, if you press type, you can select plane, which is what we're going to be wanting to draw. And you can just put in the various equations of the planes which we're using. Once we've done that, though, it'll take a little moment to draw it because it's having to think a little bit. You can get a picture of the various planes which you are looking at. And from there, you might well be able to distinguish whether it is a sheaf or whether they are the same planes, and whether it is a prism or whether there is a pair of parallel different planes as well. So gents, this week we're going to focus on exercise 6F and on the mixed exercise. I hope this video helps.